How many of you have watched Breaking Bad? Anybody? Who's the main character? Who's the actor playing the main character? Very good, Bryan Cranston. So it's easy for you to remember this. Also, there's a city in Rhode Island called Cranston. I was driving from Long Island to Boston one time, and in Rhode Island somewhere I saw a sign that said Cranston exit here. It looked like a command issued to me. I did not exit there. Let's see, last term my Tuesday office hour was at 10, and it'll be the same. And we'll have one on Thursday. At 11. Yes, Miriam.
Is it possible to have one of those office hours on a Monday, Wednesday, or Friday?
Sure.
Class, Tuesday, Thursday
At those times. Okay. Let me think of my complicated schedule for a minute.
Well, before class, we have the recitation.
How about that? Wednesday at 4. Okay. Let me tell you where my office is located. Okay, so So 10% on homework. Homework will start Monday, a week from today. Quizzes, we'll start with quizzes Friday. And 35% will be a midterm. The midterm will be about the mid of the third week. And then the final is the last day of classes, and will be held in this room. The book is... And I recommend you get the third edition. Okay. Any questions? No? Okay. Good. All right. Let's go over the test then. I apologize, the grades haven't been completely entered yet. I'm waiting for the TA to enter the grades. You should have the test back by Wednesday. I hope even later today, but we'll see. Okay, so problem 1. X has a gamma distribution. That is the density for the random variable x is this. And you had to compute these 3 things: the mean, the second moment, and the actually it was the variance, sorry. And the moment generating function. And the idea here is that since f sub x is a density, its integral is 1. That's the only thing you really have to use in this problem, which means this is equal to the gamma function at alpha over lambda to the alpha. Okay? That's the only thing you need to do this problem. And how does it work? For continuous random variables, expected value is always the integral of x times the density, dx. In this case, the density vanishes on the interval from minus infinity to 0, so we only have to integrate from 0 to infinity. X times the density, and in the density there's this constant lambda to the alpha over gamma of alpha, which I pull out. Okay. And I combine the x terms here. Getting this. And now this looks like the main part of a gamma density, but with parameter alpha plus 1 in lambda, right? And if it's alpha in lambda, you get gamma of alpha over lambda to the alpha. But now it's not alpha, but it's alpha plus 1. So what should you do over here? Put alpha plus 1 here and here, right? So this would be lambda to the alpha over gamma of alpha times gamma of alpha plus 1 over lambda to the alpha plus 1, which is, well, lambda to the alpha over lambda to the alpha plus 1 is 1 over lambda. What's gamma of alpha plus 1 over gamma of alpha? That's alpha. This is kind of factorial behavior of the gamma function. Okay, so the answer for the expected value is alpha over lambda. Now let's look at the variance. Now we've already computed the expected value of x. Here it is, so we put that in here and square it. So next we should compute the expected value of x squared, the second moment. So just as in that previous case, instead of putting little x squared there, we should put, little x there, we should put little x squared there. And so I'll jump right to the second line. And we get this. Combining the x terms. And again, this looks like the meaty part of the gamma density, but with parameter alpha plus 2 in lambda this time instead of alpha in lambda. So remember, if you have an alpha in lambda, you get gamma of alpha over lambda to the alpha, but we don't have alpha, we have alpha plus 2, so it should be gamma of alpha plus 2 over lambda to the alpha plus 2. Well, in the denominator we get lambda squared. And what about the ratio gamma of alpha plus 2 over gamma of alpha? If we use that relation up there, gamma of alpha plus 2 would be alpha plus 1 times and this would be alpha plus 1 times alpha times gamma of alpha. So we insert this here, and we see the gamma of alpha terms cancel. We get alpha times alpha plus 1. So that's the second moment. And remember, we have to subtract the first moment squared to get the variance. So the variance of x would be this. Minus the second moment squared. And that is alpha over lambda squared. Okay. And then finally for the moment generating function, this would always be the integral of e to the little t for continuous random variables with density capital F sub capital X of x. This is from here to here is just definition of expected value of a function of a random variable. And now we put in the specific density function. Which means we only integrate from 0 to infinity because the density vanishes for negative values. And we get this. now instead of combining the x terms, we should combine the exponential terms. Like that. And now this looks like the important part of the gamma density without the constants. How is it different from the gamma density? The gamma density with parameters alpha and lambda has this part for the non-constant stuff. What do we have over there? We have alpha, but we don't have lambda. We have lambda minus t. So how would this change over here? We'd have the gamma of alpha still, but down here we'd have lambda minus t to the alpha. And canceling, we arrive at that. Okay, so this problem didn't require any integration at all. Just using the fact that you know that's a density, and that means that this is true, and then if you use that for different values of alpha and lambda, you can solve the whole problem. Okay, any question? Let's go to number 2. That was number 1. X is uniformly distributed on the interval from 0 to 1. Given X, Y is uniformly distributed on the interval from 0 to X. So we pick a number at random between 0 and 1. We call that X. Then Y is some number between 0 and X chosen at random in that interval, or chosen uniformly in that interval. First question, find the first part. A, find joint density of X and Y. Okay. Do we know the conditional density of Y given capital X is little x? Because if we do, we can express the joint density as the conditional one times the marginal of x. Do we know this, for example? Right? That's what it means for capital X to be uniformly distributed on the interval from 0 to 1. It has this density. Okay? Now, if we know the value of capital X is equal to little x, what's the distribution of Y? It's uniform on the interval from 0 to x. So what's the length of the interval from 0 to x? X. So the density is constant, and its value is 1 over the length. So it's 1 over x. And what about y and x here? What should be the restrictions on y and x? Well, x is less than 1. Or less than or equal to 1. What about y? it's less than x, and it's bigger than 0. Otherwise, what's this density equal to? 0. Okay. Is that clear to everybody? Okay, so the joint density it's 1 over x times 1 if 0 is less than y is less than x, whoops, is less than 1. And it's 0 otherwise. Okay? So that's the joint density. That's part A. B. Find the marginal distribution of y, or density for y. Now, you always find marginals by integrating out the other variable when you have a joint distribution. So this would be the integral over the x variable of the joint density. Now, what should be the limits of integration here? Y is fixed, and we're integrating in x. Where does x have to be relative to y? Between y and 1. So this integral should be from y to 1. And what is this function? It's 1 over x dx. And the integral of 1 over x is log. So we get log of 1 minus log of y. Natural log of 1 is 0, so we get minus log of y. This might look a little strange. Here we have a negative. This is minus, and we're talking about a probability density. Aren't they supposed to be positive? Yeah, y is between 0 and 1, so log of y is negative, so that's why this minus sign is here. You could rewrite this as log 1 over y without the minus sign if you were squeamish. Okay. So that's the marginal density. And again, what are the limits on y here? Y is between 0 and 1. So a question on that? No? Okay. And then find the conditional distribution of x given y. Well, that's just the joint over the marginal of y. And this is 1 over x. And this is log y, minus log y. So we get this. And now what are the limits or restrictions on x and y? 0 less than y less than x less than 1. Okay. So that was part C. Part D. We need to compute expected value of capital X given capital Y is little y. This will just be the integral of little x times the conditional density of x given y. That's the definition of it. So what are the limits of integration here? This conditional density is 0 unless this happens. So the limit, we're integrating it in which variable? Y. So y should go from 0 to x. And then we get x times 1 over x log y with a minus sign dx. I'm sorry, dy. Dx, I'm sorry, this is dx, yeah, dx. Dx. And this looks like minus x over log y in the end. I'm sorry. So, oh, no. So the limits of integration I got wrong. Let's do that again. We're integrating in x. So, no, y is fixed. We're integrating in x. X goes from y to 1. Sorry. X goes from y to 1. X goes from y to 1. Here the x terms cancel. So the integral becomes just minus x over log y, and we integrate from y to 1. So we get, at 1, we get minus 1 over log y. And then we subtract the value at y, so it'd be y over log y. Or you could rewrite this as y minus 1 over log y. Okay, that's 2. Three, x1 through x sub r are independent Poisson random variables with parameter lambda, and capital X is the sum of these. Here we're supposed to compute the moment generating function for x1. This is a discrete random variable, so that means it's a sum. The Poisson random variables takes on the values 0 to infinity, non-negative integers. We get e to the tk times the probability that x1 is k. That's what you get from more or less the definition. But here the only values where this is different from 0 are when k is a non-negative integer. And what is this thing? It's lambda to the k over k factorial times e to the minus lambda. Every term in this sum has the factor e to the minus lambda, so I pull it out. And now both e to the t and lambda are raised to the power k, so we combine them. Multiply lambda times e to the t, raise it to the power k, divide by k factorial. And that's what we started with. Okay, now this series is an infinite series for the exponential function. If you had a z here, sum k equals 0 to infinity, z to the k over k factorial, that would be e to the z. So this is e to this power. And when we multiply exponentials, we add the exponents. Both have a lambda here, so we get lambda e to the t minus 1 in the exponent. E to the lambda e to the t minus 1. That's the moment generating function for Poisson. Next part was compute the moment generating function for x. This becomes a product of exponentials. These are all independent random variables now. When you're taking the expected value of a product of independent random variables, it becomes the product of the expected values. All of those expected values would be the same and equal to this. And we have that multiplied by itself r times. So here we just get this raised to the power r. That'd be e to the lambda r e to the t minus 1. So what's the and it also asks, what's the distribution of x? Well, this says it's Poisson with parameter lambda r. So x has a Poisson distribution with parameter lambda r. If x is Poisson with parameter lambda, this is its moment generating function. this is defined in an interval containing the origin. So anytime you have a moment generating function that looks like this, it has to come from a Poisson distribution. Here we have a moment generating function that looks like that with not lambda, but lambda times r. So x has Poisson distribution with parameter lambda r. And then finally, use normal approximation to find a number z, so that probably x is less than or equal to z is about 0.85. Okay, well, here x is the sum of independent random variables. So we can apply the central limit theorem to it when r is big enough, and we're taking r to be 100 and lambda equal 1. So if we subtract the expected value of x from x and divide by the square root of the variance, we'd have something that's approximately normal. So what's the expected value of x? For a Poisson random variable, what's its expected value? Lambda, and its variance is also lambda. So how do you get that? How could you compute the expected value of x? Well, you could start here and put k there and do that. Another way is, here we have the moment generating function. If we differentiate and evaluate the derivative at 0, we get the expected value. If we differentiate twice and evaluate at 0, we get the second moment. And then if we subtract the square of this first moment, we'll get the variance. So those are two ways you can do that. But anyway, the long and the short of it is that the expected value of x is lambda, or its parameter, and its parameter would be lambda times r, which is 100. And if we divide by the square root of its variance would also be its parameter, which is again 100. This is approximately normal. It's approximately normally distributed with mean 0 and variance 1. That's the central limit theorem. So starting with the probability capital X is less than or equal to z, we should subtract 100 from both sides. And divide by 10. Okay, then this is about equal to the probability that capital Z is less than or equal to little z minus 100 over 10, where Z has a distribution which is normal, mean 0, variance 1. And we want that to be equal to 0.85. So you go to the table, which was on the last page, and find that if I look for 0.85 in here, it's about 1.04. Z minus 100 over 10 should be equal to 1.04. And then you solve for z. Multiply by 10 and add 100. So if I multiply by 10, this becomes 10.4, 110.4. Okay, any question on this problem? number 4. Maybe I'll wait to do number 4 after I review chapter 7. I'm going to do a little review of chapters 6 and 7. And 4 was from 7. I'm doing that because some of the students are newcomers and haven't seen 7. May not have seen 7. In fact, I'd say it's likely that they haven't seen 7. Okay, so let's go to number 5. X and Y are independent, exponentially distributed with parameter 1. So that means that their marginal densities are given by these, and their joint density would be what? For independent random variables, the joint density is the product of the marginals. Okay, and here you're supposed to find the joint density of x plus y and y. I'm sorry, I misspoke. Not x plus y, y. X over y, y. Okay. So here we have u is a function g1 of xy equal to x over y. Little v is a function g2 of x and y, and it's actually equal to just y. To invert these, x is equal to a function of u and v, h1 we'll call it. How do we get x if we know u and v? U times v is x. And y is another function of x and u and v, sorry. How do we get y if we know u and v? Well, it's just v. Now we need to compute the Jacobian of g. Well, dg1 dx is 1 over y. dg1 dy is minus x over y squared. dg2 dx is 0, and dg2 dy is 1. So the determinant here is 1 over y. Okay. And the change of variable formula for the density says that the density of u and v at little u and little v is the joint density for x and y evaluated at h1 of u v, h2 of u v, and then 1 over absolute value of the Jacobian evaluated at h1, h2. Okay, that's the change of variable formula. Here's the joint density for x and y. So we evaluate that where? At h1 and h2. What's h1? It's u times v. What's h2? It's v. So we get e to the minus uv plus v. And then 1 over j at h1, h2. So this would mean what? This is the y, that's the x. So j would be 1 over h2, right? 1 over absolute value of h2. h2 is 1 over, yeah, so it would be 1 over, what would this be? This would be 1 over h2 in the denominator, so it becomes h2 in the numerator. It would become h2 here, but what's h2? It's v. So we get times v here. And this is what? 0 less than u less than infinity, and 0 less than v less than infinity. Okay, so that's the joint density. Let me simplify it just a little bit. Okay, let's find the marginal. So that's part A. Part B, find marginal density of u. Here we just integrate out the v variable. How do you do that? Well, what are the limits of integration going to be? It's from 0 to infinity. And what does this look like? This looks like the gamma density with parameter alpha equal 2 and lambda equal to 1 plus u. This is we're getting the gamma density. What does the gamma density look like again? Remember that was it was lambda to the alpha over gamma of alpha, x to the alpha minus 1, e to the minus lambda x, right? Could also express it with u's. Or v's, I guess. Maybe I should just use v here. Can we make the thing in the box here look like this by appropriate choice of alpha and lambda? How do we get a v to the first power from over there? How can you make alpha minus 1 equal to 1? What do you choose alpha to be? 2. If alpha is 2. And how do we pick lambda to get this? 1 plus u. So this integral would become gamma of 1 plus u over alpha is, gamma of alpha, that's 2. Gamma of alpha is 2 over lambda, that's 1 plus u, to the alpha, which is 2. And what's gamma of 2? It's 1. Gamma of 2 is 1. And so this becomes 1 over 1 plus u squared. Okay. And then finally, part C, what's the probability x is less than y? Or probability x over y is less than 1. These are continuous random variables, and they have the same distribution. So what would be the difference between this and the probability that y is less than x? That'd be the same. What's the probability that y is equal to x if they're independent? 0. So what should this probability be? Half, because this plus probably y is less than x adds up to 1, and they're equal. So the answer here is half. You actually don't need to know the density. But if you integrated this from 0 to 1, that would also give half. Okay. All right. Okay, let's do one more before the break. Number 6. Any questions so far? Here we have a lot of random variables. Almost Avogadro's number of random variables. So this means that probability that xi is 1 is p, which is 1 minus the probability xi is 0. Okay, and then p here is 2 over 10 to the 23. Very small. But p times the number of random variables is about 2. It is 2, actually. So we can use the law of rare events. It says that if we add up all those, it'll be approximately Poisson with parameter 2. Okay, that was the law of rare events that we did. Remember in the review session we talked about atoms emitting alpha particles. There are about 10 to the 23 atoms in a block of any substance. Whether an individual atom emits an alpha particle or not is a Bernoulli random variable. That is, if it does it within an hour, say, with some parameter p. P is very small, something like this. The atoms are acting independently, so that means all these things would be independent. This would be 1 if the first atom emits an alpha particle, 0 otherwise. This would be 1 if the second one. So that was the example we were talking about on the Monday before. So and this is capital X. So then the probability that x is less than or equal to 2 would be, well, the probability that x is 0, plus the probability that x is 1, plus the probability that x is 2. Probability that x is 0 for, what's the probability that x is k if x is Poisson? Well, it's going to be 2 to the k over k factorial e to the minus 2. Right? So when we put k equals 0 here, we get e to the minus 2. When we put k equal 1, we get 2 over 1 e to the minus 2. When we put k equal to 2, we get 2 squared over 2 factorial times e to the minus 2. So this would be 1 plus 2 plus 2 or 5 times e to the minus 2. Okay. What about the expected value of x? Well, since this is approximately Poisson with parameter 2, this would be about 2. And what about the variance of x? Well, again, for Poisson, the variance and the mean are both the parameter, so this is also about 2. Okay, so let's take a 10-minute break, which is what we'll always do, take a 10-minute break about this time. Reconvene, then we'll finish this up and then do a little review. Okay, well, that's approximately 10 minutes. Let's try number 7. Here, the joint density of two random variables is given by e to the minus y when x is between 0 and y, or y is bigger than x. Okay? And it's, of course, 0 otherwise. So we have to compute the covariance of xy, which is the expected value of x times y minus expected value of x times the expected value of y. So we have to compute these three things. To compute this, we need the marginal density for x. To compute that, we need the marginal density for y. And this we can do with the joint density for x and y. Since we have that already, let's do this first. This would be the double integral of little x times little y times the joint density. Now, what are the limits of integration? What region in the plane is described by 0 less than or equal x less than or equal y? What pairs, little x, little y, satisfy that? Yeah, so this is in the first quadrant, obviously. And if we draw where x is equal to y, that would be this, the line y equal x. Now, where would a pair x, y have to fall in order for the second coordinate to be bigger than the first? Well, that's above, right? So it's this region up here. And we want to integrate over that region. Okay. So how do we describe that? Well, what does y do? It starts at 0 and goes to infinity. So here we have 0 to infinity. But now for a fixed value y, what does x do? Well, according to that, you can see x goes from 0 to y. See, for a fixed value y, like this one, x values go, we go across this line here, right? What do the first coordinates on this horizontal line do? They go from 0 to here is where y is equal to x, they go to y. Okay, so we have that for the limits of integration. Now let's substitute the value for the density. It's e to the minus y. Okay. And if we integrate the x first, we get x squared over 2. Right? Integral x dx is x squared over 2. Be evaluated between 0 and y, you get a half out in front here, integral from 0 to infinity. So you get a y squared times y would be y cubed, e to the minus y dy. And now what's that equal to? Here we're integrating the meaty part of a gamma density again, right? With alpha equal to what? 4, and lambda equal to 1. So what's that's going to be, it's gamma of 4 over lambda to the 4th, right? Or 1 to the 4th. Right? This is remember the gamma density? Integral from 0 to infinity, y to the alpha minus 1, e to the minus lambda y dy is equal to gamma of alpha over lambda to the alpha. In that integral there, how do we get alpha minus 1 to be 3? Alpha should be 4. And how do we get lambda y to be y? Lambda should be 1. So what's 1 to the 4th? It's just 1. Gamma of 4 is what? 6. This is 3 factorial. 3 factorial over 2 is 3. Okay. So actually, I think in this whole test, you never had to do an integral. All you had to know was the...
Yeah, you did the one for...
I had to do one?
It's 1 over x, 0 to y.
Oh, I was wrong, yeah. You had to integrate 1 over x dx. Yeah.
Cool. That is cool. And this one right here, too.
Oh, yeah, you had to integrate x. Okay, you had to integrate x dx and 1 over x dx, yes. Okay, so I take it back. Okay, so what else do we have to do? We have to compute expected value of x and expected value of y and multiply and subtract from here. So to get the expected value of x, we need the marginal density. Okay, I think we're going to have to integrate again. Okay, so let's get the marginal for x. We integrate the joint. And what are the limits of y going to be? X is fixed, y then does what? Goes from 0, no, not 0, but x to infinity. So we integrate from x to infinity e to the minus y dy, and that's e to the minus y evaluated, oh, minus, I'm sorry, between x and infinity. At infinity, the value is 0. Subtract the value at x. That'd be subtracting minus e to the minus x, you get e to the minus x. So the marginal density for x is e to the minus x. This is when x is positive, so that's an exponential random variable, right? So what's the expected value of x? Expected value of an exponential with parameter lambda is, so we get 1 here. If you didn't remember that, you'd wind up integrating x times e to the minus x dx, right? It'd be x times the density. And what's this integral? Well, again, you could use the gamma density, because this is gamma with alpha equal to 2 and lambda equal to 1. So this would be gamma of 2 or 1. Now let's get the marginal density for y. That means we should integrate the joint density in the x variable. And what should be the limits of integration here for x? Y is fixed. X goes from 0 to y. So we integrate from 0 to y, e to the minus y dx. This doesn't depend on x, so it's just integral of 1 from 0 to y dx. That would be y e to the minus y. So there's the density for that. So what's expected value of y? Again, this is looks like the important part of the gamma density with parameter alpha equal 3 and lambda equal 1. So this would be gamma of 3. And at the integers, gamma of n is n minus 1 factorial, so this would be 2 factorial or 2. So expected value of x is 1, expected value of y is 2, expected value of x times y is 3. So covariance of xy is 3 minus 2 or 1. Okay, now let's compute the expected value of x given capital Y is y. This would be the integral of little x times the density, conditional density of x given y dx. Now we need to compute this conditional density. And that's the joint over the marginal. The joint is e to the minus y. The marginal is y e to the minus y, which is 1 over y. And what are the limits here? Where is this different from 0? When 0 is less than x is less than y. Okay? So the conditional distribution of x given capital Y is little y is what? What would you call that? Uniform on the interval from 0 to y. So coming back up here, what are the limits of integration then? We're integrating in x. X goes from 0 to y. X times 1 over y dx. Integral of x dx is x squared over 2. Evaluated at y would give y squared over 2. But then we have a what? 1 over y, so that would be y over 2. And what about the value at 0? That vanishes. You might have just written down from here, if a random variable is uniform on the interval from 0 to y, what's its expected value? It's the midpoint of the interval, right? Y over 2. Okay, and the other part was the other conditional expectation, I think. Here we integrate y times the conditional density of y given x dy. So we need this conditional density. That's the joint density divided by the marginal in y. I'm sorry, in x. This is e to the minus y, where it's different from 0, it is. And what was this? E to the minus x. So I'll rewrite this as e to the minus y minus x in parentheses. And this is for 0 less than x less than y. Okay? And so the conditional expectation what are the limits of integration here? Little x is fixed. What does y do? Goes from x to infinity. Okay. Well, we could maybe change variables, z equal to y minus x. Then this becomes integral from 0 to infinity, z plus x e to the minus z dz. Do you agree with that? Okay, so we have two integrals, z times e to the minus z dz. And what's that? That's 1, because it's a gamma thing again, right? And then x times integral of e to the minus z dz, that would be x. Okay. The final part here is identify the distribution of the random variable expected value x given y. Well, here, let's call this little g of y. What is this equal to? This is y over 2. Okay. So what would be the expected value of capital X given capital Y? Well, that's just g of capital Y. And what would that be? That's capital Y over 2. Now, what's the distribution of this? We need to know the distribution of y, I suppose. And where's the marginal y? Right here. Okay. So let's compute the distribution function. Let's take the derivative. That'll give us a density. And what do we get here? Do we know what the derivative of this is? Well, it would be the density of y at 2y times the derivative of 2y with respect to y, which is 2. What's the density for capital Y? It's little y e to the minus y. So here we get 2 times 2y e to the minus 2y. And this is for 0 less than y less than infinity, which would be 4y e to the minus 2y. What's that distribution? Does that have a name that we know?
Gamma.
Gamma with parameter what?
2 and 2.
Here, how can we get a 2 out of alpha minus 1? Alpha has to be 2, and lambda is 2. So it's gamma with parameter 2 and 2. Okay. Okay, next one, x and y are independent geometric random variables with parameter p. This means that their PMFs are given by that. Compute expected value of x and the variance of x. That would be the expected value of x. This is k times the probability x is k. We can factor out a p. And about the only series that we ever, well, I guess we used 2 series in this class. The 2 series were these. That one. The other one was this. the one for exponential and the geometric series. But I think those are the only two we ever used, right? This almost looks like the geometric series. What if I differentiate this with respect to r? What would it look like? If I differentiate term by term, I get k r to the k minus 1. And keeping in mind that there's a minus here, this is equal to this. Which would be minus p derivative with respect to p of, this is the r now. So it'd be 1 over 1 minus p, which would be minus p times the derivative with respect to p of 1 over p, which is minus p, and then this would be minus 1 over p squared. So that's 1 over p. Okay? The variance of x is expected value of x squared minus the square of the expected value. So we know this, so we need to know this. This is a little trickier. Why did I do that? How did we get the first one? By differentiating. If we differentiate again, if we differentiate this twice, what does the second derivative of this look like? Right? And how do I compute this second derivative of this? Well, I compute the second derivative of that. Okay? So I want to get this into look like the second derivative somehow. But I don't have k times k minus 1. I have k squared. But that's never stopped us in the past. I often just change it to what I want, right? First of all, where does that series for the second derivative start? At 2. This one starts at 1. So let's kick out the k equal 1 term here. What is this when k is 1? It's 1, and then 1 minus p to the minus 1. And then we'll start at 2. Now, k squared is k times k. K is k minus 1 plus 1. I don't think you'll disagree with that, right? this first term is p, and we get plus p, 1 minus p, sum k equal 2 to infinity, k minus 1, 1 minus p to the k minus 2, and then plus p, 1 minus p, sum k equal 2 to infinity, k times 1 times 1 minus p to the k minus 2. All right. Now this looks pretty good. That's the first. I'm going to put this first. This term is exactly this. When I differentiate the first time, I get a minus from the chain rule. When I differentiate the second time, I get another one, so it goes away. And so that would be that. I have this p here. This is almost, let's see. I'm going to put this over here. And I'm going to put the 1 minus p back inside. All right, when I multiply 1 minus p times this, I get this. Okay? This sum is 1 over p. What happens here, the k equal 1 term is not there, but what would it be if I put k equal 1 in here? What is it? What is this when k is 1? That's 1. This is times p. Do we have it? That's it. That's the k equal 1 term. So I can change this to p sum k equal 1 to infinity k 1 minus p to the k minus 1. In other words, I can put this in here, and that's the k equal 1 term. So this is p 1 minus p d squared dp squared 1 over p plus p times minus. Well, we just did this, didn't we? Didn't we do this? Isn't that that? And what do we find that was? 1 over p. Okay, so we differentiate this twice. First time we get minus 1 over p squared. Second time we get 2 over p cubed. So this is 2p 1 minus p over p cubed plus 1 over p. That's expected by x squared. And we subtract 1 over p squared, and we get the variance now. Let you do the algebra. Okay, there's a little trick there. Another way to do this is you can compute the moment generating function for geometric, which is pretty easy. How do you get the variance from the moment generating function? You take the log, differentiate twice, and set t equal to 0. Okay, that gives the variance. So there's another way to do that. Compute the PMF of x plus y. Okay, well here you could do two things. What's the interpretation of a geometric random variable? It's the number of right number of trials it takes to get a success when you're doing independent Bernoulli trials, and the probability of success is p. So these are both number of trials to get a success, right? So what would x plus y be number of trials to get what? 2 successes. So what's the probability that the number of trials to get 2 successes is k? Well, if I'm thinking in terms of success and failure, if it takes k trials to get 2 successes, the last trial had to result in, the kth trial had to result in a success, right? What else has to happen? In here, there have to be k minus 2 failures and 1 success, okay? So there will be altogether k minus 2 failures and 2 successes. If I fix one particular sequence like that, say S, all F's, and then S, what's the probability of that sequence? Well, for the S's, we get a p squared. For the failures, we get a 1 minus p to the k minus 2. And it didn't matter, actually, where the S's and F's were. No matter how you do it, the probability of any sequence with 2 S's and k minus 2 F's would have that probability. Now we have to count how many sequences are there where there's an S here and only 1 S there. Is there any choice about this? How many choices do we have? 1 choice there. Okay, so how many choices do we have here?
K minus 1.
K minus 1. Okay, so that's it. You could also use the formula for the PMF for sums of variance of x times y. Would be that. They're independent. And this is 1 over p squared, and this is 1 over p squared, so this is 1 over p to the 4th. And then variance of x is the same as variance of y. Expected value of x is the same as expected value of y. I'm sorry, this b square should be inside here. So this would be the variance of x plus expected value of x squared, quantity squared, these two being the same, minus 1 over p to the 4th. And then you substitute in the value that you found there for variance of x. Or if you left it like that, it would be fine. And finally, number 9. X is binomial with parameter n and p. What's the expected value of x? Well, it's, do you remember, how do you represent a binomial with parameter n and p? It's the sum of n independent Bernoullis with parameter p. Expected value of a Bernoulli with parameter p is p. Sum of p n times would be np. What's the variance of x? Well, the variance of independent random variables is the sum of the variances. The variance of the sum of independent random variables is the sum of the variance. What's the variance of a Bernoulli? P times 1 minus p. So the variance of a sum being the sum of the variances for independence, you get np 1 minus p. Okay. And the last problem is just a central limit theorem. What's the probability that x is less than 59.8? This would be probably x minus n is 50, n is 100, p is a half. So x minus np, that'd be 50, over the variance, that'd be square root of 100 times p times 1 minus p. I'll write it this way for a moment, is less than 59.8 minus 50 over square root of 100 times p times 1 minus p. And what's p in this case? It's a half, so p times 1 minus p is a fourth. So 100 times a fourth is 25. Square root of 25 is 5. So this is the probability that x minus 50 over 5 is less than 9.8 over 5. 5 into 9.8. What? 1.96? So this is probably that this thing is less than 1.96. What a coincidence that it came out to be that, because that's 0.95, isn't it? Or is it 0.97? 975? 975. Yes. What are the chances of that? That it would be exactly one of the numbers in the table. Okay, so that's one. So the 0.975, I guess. Okay, so that's the end of the final. Any questions on anything? Okay, the killer problem was number 8. It had a longer computation. But for those who just came into the course, this is a kind of a good reference to about what we learned in the last 5 weeks. And for those that are going on, this is the stuff you should have mastered. If you haven't, go over it again. Come ask me questions. Okay. It was a long test. I give long tests. I give hard tests. If you do well, you should feel great. If you don't despair. There's always a chance to improve. Okay, so let's review a bit. I think I'll start with chapter 6. So I highly recommend, if you didn't take 131A last term, to read chapter 5 about the central limit theorem, because we're going to be using that frequently. Okay, now in chapter 6, it starts out with, usually we'll use z to denote a normal random variable. And if we're going to denote a bunch of them, we do z1 through zn. Okay, so this will be normal, mean 0, variance 1. And then we define u to be z squared. This is a chi-squared random variable with 1 degree of freedom. So the square of a normal random variable with mean 0 and variance 1 is chi-squared. And just to be precise, that z is normal with mean 0 and variance 1 means that the density for z is this. Okay. Which means that probability z is any set B is the integral over B of the density. Okay, if that's the definition. Any random variable that has the same density as this, or the same moment-generating function of this, will be called chi-squared with n degrees of freedom. So this symbol here means the distribution of u is chi-squared with n degrees of freedom. So that means it has the same PDF. Did I say PMF a moment ago? But it has the same density. If u has the same density as this, then u is called chi-squared with n degrees of freedom. So if u is chi-squared with n degrees of freedom, so in other words, it looks like the sum of the squares of n independent normal mean zero variance one random variables, and z is normal with mean 0 and variance 1, and u and z are independent, then z divided by square root u over n is, or has, well, it's called a Tn distribution. A T statistic with n degrees of freedom. So we'll be working with this kind of random variable. You can look in chapter 5 for the densities for chi-squared and t. Oh, I'm sorry. I was wrong. Chapter 6. You can look in chapter 6 for the densities. I don't think you have to memorize them. Could be that you work with them often enough that you do without intending. Memorize them. Another common distribution is the following. If u is chi-squared with n degrees of freedom, v is chi-squared with m degrees of freedom, and u and v are independent, then u over n divided by v over m has an FMF. I think it's, I'm not sure I have these in the right order. Is it n, m? N is the number, yeah.
In the book it has it as u is chi m squared and v is chi m squared.
Oh, okay. Maybe I should, well, I'll leave it like this. Okay. So I'll call this y. And you can look up the density for that. We did a problem in the final about the density for a ratio. One of the exercises in the book is to find the distribution for 1 over y. And what would that be? Well, what happens when you take 1 over y? This goes in the numerator, and this goes in the denominator. So that would be Okay, so that's kind of a review of chapter 6. I would recommend doing some of the exercises to get used to these distributions. They'll be used in analyzing data from samples. Suppose that x1 through xn are IID. This is an abbreviation we'll use commonly. Independent, identically distributed. Normal, mean mu, variance sigma squared. X bar equal 1 over n, sum I equal 1 to n of xi has what distribution? Well, we know the sums of independent normals is normal again. And how do you establish that? What tools do we have for identifying distributions of random variables? Moment generating function. If we take the moment generating function of a sum, let's forget about that for a moment, of independent random variables, it's the product of the moment generating functions. What's the moment generating function of xi? It's that. So what's the moment generating function for x bar? I did 2 or 3 steps here. What steps did I do? I wrote x bar as 1 over n, this sum, right? I put the 1 over n with the t. Then I'd have e to the t over n times the sum of the xi's. Where that would be the product e to the t over n x1 times e to the t over n x2, etc., times e to the t over n xn. And I have expected value of that product, but these are independent, so it would be the product of their expected values, and they're all the same. So I could put 1 here, I guess. And I get n things like this multiplied by each other, so I get this thing to the n. We've done that several times. So what is this thing? According to that, it's e to the mu t over n plus sigma squared over 2 t over n squared. That's the thing inside the parenthesis, and we raise that to the nth power. And now we multiply the exponent by n when you do that. So this becomes e to the mu t plus sigma squared over 2. Maybe, can I just change this a little bit? I'm going to write the same thing, but I'm going to put the 2 under the t squared. Because then the coefficient of the t squared over 2 is the variance. Okay? And I'm going to do the same thing here. Put the 2 there. Now when I multiply this by n, this is an n squared, actually. And what else do I get? I get t squared over 2. And what's the coefficient of t squared over 2? Sigma squared over n. So that means that x bar is normal with mean mu and variance sigma squared over n. Okay? I think this is still chapter 6, by the way. The sample variance is this. And in this case, the sample variance, if I multiply by n minus 1 and divide by sigma squared, this is chi squared with n minus 1 degrees of freedom. Okay, and an important additional fact about x bar and s squared when you have independent normals is that x bar and s squared are independent. So we're almost in that situation there, where u is going to be n minus 1 s squared over sigma squared. And z, well, we can't use x bar. Z is normal with mean 0 variance 1. So we have to turn x bar into a normal random variable with mean 0 variance 1. If you have a normal random variable with mean mu and variance sigma squared, how do you convert it to a normal with mean 0 and variance 1? You subtract
Subtract the mean, divide by the square root.
right. Subtract mu, divide by
Sigma.
sigma. So we should take x bar minus its mean, which we found was mu, divide by its variance, square root of its variance, I mean. So that'd be sigma over root n. This is normal with mean 0 and variance 1. This is chi squared if we do that. So x bar minus mu over sigma divided by root n divided by square root. That's our u. And now we have to divide by the number of degrees of freedom. This is going to be a t statistic with n minus 1 degrees of freedom. Let's simplify this a bit. This n minus 1 and that n minus 1 cancel. Also, there's a sigma in the denominator and the numerator, and there's a sigma in the denominator and the denominator. That means they cancel. And so we get x bar minus mu over root n s is a t statistic with n minus 1 degrees of freedom. The guy took care of everything. Okay, so this will be a typical, we'll use this in the future. A lot of times we can assume we're sampling from normals and that the samples are independent. And we can analyze our sampling using this ratio.